me. Okay, so good afternoon, everyone. I am here to talk about something called inferred reality. This is a term that we cooked up at AMD. And like Johannes said, I lead research into neural rendering and generative AI. So what am I planning to cover today? We start with defining what is neural rendering and why is it important in the context of real-time graphics. Next, we'll define what is inferred reality, and I'll present the transformational stages that we could take to go from the current state of the art to inferred reality. In the process, I'll cite some evidences from research papers, from industry, and from academia. Although I'm not putting a date on when this research will mature, when the graphics community would embrace this new reality, I believe it will be like a multi-year journey to get there. All the research techniques that I talk about in this new paradigm of rendering should be considered as tools in a toolbox. The game developers or the ISVs, they can pick whatever tools that they want to put in their toolbox that best fits their pipeline. So one size will not fit all. At the end, I have a few call to actions for the graphics community has to take to adapt to this new reality in computer graphics. With that, we are all witnessing an evolution of rendering as we move from rasterization to hybrid rendering to path tracing. And we want to be able to generate accurate, physically based effects, realistic lighting, materials, and shadows. So we are also starting to take advantage of hardware ray tracing and machine learning acceleration to render physically accurate photorealistic frames. As we push towards increased realism, rendering transparent, glossy, reflective objects, thin structures, high-density animated geometry like foliage, subsurface scattering, specular effects, hair, fur, all of these, they push the boundaries of classical computer graphics algorithms. Plus, we are also hitting technology headwinds. Moore's law does not scale anymore, and we no longer see it help improve performance per dollar. And traditional graphics scaling will not meet the cost, power, and thermal needs. So we have to come up with a new paradigm of rendering with ML, and this is becoming prevalent. So as path tracing quality is becoming closer and closer as a target, investing into classical methods will not get us to the real-time speeds that we want. So ML acceleration seems to be a must. So this brings us to the topic of neural rendering. So let's define neural rendering. It basically combines ideas from classical computer graphics and machine learning to create algorithms for synthesizing images from real-world observations. So the idea here is to employ neural networks to accelerate, augment, or substitute parts of the rendering pipeline to achieve the photorealistic immersive visuals that we want. So the title of my talk is Inferred Reality. So what do I mean by that? Imagine if we can get to an image that cannot be distinguished between a game rendering versus a film rendering. So that's a highly photorealistic, great lighting, realistic reflections, shadows, subsurface scattering, and other global illumination effects from the current state of the art using AI models at an interactive or real-time speed. So I'm calling this as inferred reality. The next few slides, I'll talk about the current state of the art technologies and lay out a potential set of transformative steps that is being explored in research to get to this inferred reality. Okay, so the first stage is to replace post-processing with neural networks. The main idea here is to, because AI can do better than simpler heuristics, so just take whatever heuristics you have and replace that with the AI model. Generally, these models have deeper topology. Either they are CNN-based or transformer-based models, and they run once per frame. And some examples of these are upscaling, supersampling, and denoising. So most of you all should be very familiar with this. Here I'm showing a comparison of native 4K rendering versus FSR 3.1 performance mode, and then FSR 4 with ML accelerated in performance mode. So if you look at the foliage and the rock, FSR 4 shows more detail, water looks more closer to native, and fire looks more physically accurate with the ML accelerated FSR4. Again, another example, the right-hand side is AI for upscaling, and then observe the details on the backpack, the foliage, the grass blades, the definition on the ground, the wires on the right. So they all look amazing on the right-hand side. So let's move to the next section, denoising. So this is an ML technique that we built where we combined denoising with upsampling and super resolution. So from left to right, given a noisy, aliased, low-resolution rendering, this ML model generates denoised and upscale frame within a few milliseconds, while the ground truth render for the same would take order of minutes. So depending on the use case, a denoised-only output can also be generated from this model, which is identical to doing 1x upscaling. We have posted a blog that we wrote on this technique, so you all can go check it out offline. Okay, here are some details about our technique. So the input includes noisy color rendered at 1 SPP and a few guiding buffers that are readily available in any rendering engine, like albedo, normal, roughness, depth, specular hit distance, etc. at low resolution. History output is also reprojected by motion vectors for temporal accumulation. The neural network predicts multiple filtering weights and decides how to temporally accumulate, denoise, and upscale noisy low resolution. So this research also replaces multiple denoisers by denoising all noise in single pass. So check out the paper that we published on this technique at i3D early this year. Okay, here is a video showing the temporal quality with a 1 SPP input at 1080p resolution and denoised upscaled output at 4K resolution. So if you can see the top box there is the input, and then the rest of the video is the output. Well, these are some of the examples from the first stage of our journey towards inferred reality. Now let's get to the second stage of the journey. I am calling this next stage as inline neural rendering. This stage, we employ tiny neural networks, also called multi-layer perceptrons, at the heart of the rendering pipeline to approximate radiance, shape, material, texture, etc. The neural networks faithfully reproduce the effect that they are trained on. They're small and generally 2 to 3 hidden layers. They fit inside a shader really well. They're fast to run, and they can run in real time. And in some cases, they are more efficient than physically based shading. So such neural networks can either run once per ray or multiple times per ray, or once per pixel or multiple times per pixel. So here is an example of how a neural network is used to approximate radiance. So in traditional rendering, we do multiple bounces, and then we employ analytical cache. Instead, a tiny neural network is trained in the order of a couple of milliseconds while we are rendering the frame, and then the trained neural network is used to compute the final pixel value at a given position and viewing direction, while being completely agnostic to the scene's lighting, material, and geometry. So as you can see on the images on the right, the neural radiance caching generates less noisy output compared to employing an analytical radiance cache. And I'm referencing a paper from NVIDIA here. Okay. The next technique, next example where we are applying tiny neural networks is to approximate complex geometries. So in conventional path tracing, we find the ray geometry intersection. So this is typically accelerated with a BVH. And BVH traversal exhibits irregular execution patterns with branch divergence and unpredictable memory access, making it computationally expensive, especially when the BVH is deep. So the method that we are working on, called the locally subdivided neural intersection function, is a neural geometric representation which can be injected into a scene with other geometries. So you can think of this as a replacement to BLAS, and results in less divergence, better execution efficiency, and smaller memory footprint. The bottom left image is a scene with objects with low geometry complexity, which are rendered using BVHS and triangles. The complex geometries are baked into LSNIF, and it can be rendered together with regular triangles as shown on the right. Okay? The third example is to use neural networks for texture compression. There are two flavors to this topic. The first one is neural texture block compression. This is employed to reduce disk space. The neural network is run at low time, and the model runs standalone. No need of any runtime shader changes in this. And here is a paper that some of my colleagues published on this research topic. And then the next one is the neural texture compression employed to reduce VRAM footprint, and it runs on texture or texture set fetch and needs runtime shader changes. Okay, the last example in this category is neural materials. So some materials can be very challenging to render in real time. So especially layered materials consisting of a stack of materials, each of it having its own high-resolution texture and exhibit complex interactions between the layers. So we use an autoencoder to map these materials into latent space, and then we create a pyramid of latent textures. The latent textures are then evaluated using an MLP to obtain the BRDF in real time. And irrespective of the complexity of the initial material, and due to the fixed size of the MLP, we end up with some constant evaluation time and constant memory cost. So this approach was mainly described by the NVIDIA paper that I've quoted here at the bottom middle. The approach can be combined with neural texture compression to reduce the memory cost. So for example, one promising approach is to compress the block compressed neural textures directly during the training phase. So that's the paper from Ubisoft at the bottom right. Okay, so we talked about two techniques now that's kind of state of the art at present. So let's see what happens if we combine some of these techniques from both the state of the art methods into a pipeline. So here are some results. Here is a 1SPP part traced frame from a demo called Hanger. And we add neural radiance caching on top of it. And this is the image that we get. And then you add the neural supersampling denoising on top of it and cleans up everything. And you get a very good quality part traced output. So now I'm moving on. There are some limitations to neural inline rendering. And although these tiny neural networks can faithfully reproduce the effect that they are trained on, they're pretty efficient with that, but there are limitations that we need to work around. The first one being it does not capture high-frequency data. So you need some kind of encoding, input encoding, like either positional, hash grid, or something else. And then they have difficulty to handle topological changes or deformations. They also have difficulty to handle dynamic lighting, transmissive materials like subsurface scattering and all that. And training cost could be high. Some examples, such as neural radiance caching, they employ online training. So obviously, you cannot train at PyTorch level. You have to rewrite the code, the training code in either HLSL or C++. And we need to employ online training. So that could be quite high. So these are some limitations of neural inline rendering. OK. So we are past the current state of the art. Now we are entering into some early ideation territory. So in this transformation stage, we want to see if we can use AI methods to replace costly computations, like global illumination, or effects like caustics, or mirror reflections, or transparency, and things like that. Okay. These are two images that show many global illumination effects, mirror, glossy reflections, interreflections, caustics. Not as much on this picture, but specular effects, shadows. My colleague rendered this image on the left at 120K samples per pixel with 5.7 trillion rays and at 2K resolution. And it took about 4 hours to render this one frame. In order to improve the speed of regular ray tracing, obviously we already saw we can use raster to sample important parts. We can reduce the number of bounces using neural radiance caching, and then jointly denoise and upscale. We are very smart about how much computation we want to spend in ray tracing and how much we want to spend in machine learning to get to a photorealistic image. But I wanted to see what happens if I use a generative AI model here, right? Can I get to an image that is closer to the one on the left and with a similar cost and without much inaccuracies? So this is what I did. When I gave the prompt that's written there, pushed it through a Gen AI model, it generated that image on the right at about 2 seconds. Definitely looks more impressive, but then it lacks physical accuracy. So you will probably notice the reflection of the ring is bigger than the ring itself. The shadows, the dragon could be a bit more defined, right? But what if we can control the hallucination, and with some targeted fine-tuning, can we leverage the success of these large-scale generative AI models to generate photorealistic images without any explicit understanding of PBR? So that's the next area of research that we are heading towards. Okay, one of the first works to utilize neural networks for rendering is deep shading. This came almost a decade ago, and it takes auxiliary buffers as inputs and predicts the final shading with the help of a CNN model. Another relevant work is deep illumination. It uses GANs, which is another different type of a generative model to predict global illumination. And recently, the XRGB proposed new ways to convert a real image to auxiliary buffers and back, and then it uses a diffusion model for this particular purpose. So let's look at what are diffusion models. So given an image, in this case, an image of a puppy, we can keep adding Gaussian noise until the image completely disappears. It's not practically useful onto itself, but if we can train a neural network to reverse this process, so given a noisy image, we can ask the neural network to remove the noise little by little. By repeating this step again and again, we can go from pure noise to some realistic image. And the final image will depend on what kind of noise being used in the initial phase. So you can generate many unique images because of that. Now, okay, my clicker doesn't want to work now. Okay. So one of the main ideas in diffusion models is to not do the diffusion step in color space, but instead do it in latent space. So why? Because the latent tensor is much smaller and makes the diffusion process much quicker. And after we get the final latent tensor, we push it through a variable autoencoder, and then we decode that to another image. So there are two different backbones we can employ, a transformer backbone or a unite backbone. And there are two divisions in the transformer backbone. You could use the DIT or the VIT backbone. I'll skip introducing these things because that itself will be another talk. Okay, so as I mentioned previously, caustics are one of the most complex global illumination effects. So in our research, we wanted to come up with a way to compute caustics using a diffusion model. So here is our architecture that we built. We used a pre-trained stable diffusion model. We started off with SDXL, and currently we have moved on to SD 2.0. We use a VAE to encode the auxiliary buffers like direct illumination, albedo, normal, radiance, skews, and we pass that as a condition to the unit. We also encode the light direction with spherical harmonics, and then the light position using positional encoding. And then all of this goes to the unit, and then it does the denoising loop. And instead of predicting the global illumination directly, we predict an intermediate buffer, which we modulate by albedo and add the direct illumination to that. So we found that this gives us better results than predicting the global illumination directly. Again, we published a short paper on this in Eurographics this year. So here are some results from our research. As you can see, we are able to generate quality caustics with just direct illumination as input and a few GBFers. And we are also able to control hallucinations and achieve pretty good spatial and temporal stability. Our plan is to extend this technique to handle other complex GI effects in future, like mirror reflections and transparency, etc. Sorry, I don't know why the bottom one isn't playing. Okay. Moving on. So now I want us to foray into a new frontier of agentic or self-aware objects. So these are fully autonomous, self-aware objects, and they're trained with behaviors on how they interact with the environment. They're high-quality agents, and they preserve geometry. They adhere to accurate physics and animation. So why am I getting to self-aware objects now? So think of this situation where you have a robot. Its function is to build and repair another robot and use tools. It interacts with its environment, also with another robot. It's aware that hey, there's no juice in that robot, so it needs to find a battery, and it cannot proceed with the repairs without that. And then if you noticed, it pats on the robot when it finds out that there's no juice. It's showing emotion and empathy. So a developer needs to program all these behaviors, right? Whereas what if we can make the robot a self-aware object, and it can infer these behaviors instead of the programmer has to specifically program for all these behaviors. So one of the ways to create such self-aware objects is to use the technique of reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions in an environment to maximize the cumulative reward. So it's like teaching AI to learn through trial and error and receiving feedback for its actions and adjusting its behavior accordingly. Or we could use imitation learning, which is also known as learning from demonstration. So here is where an agent learns to perform a task by observing an expert's actions and mimicking those actions. So AMD, we recently released this reinforcement learning platform called Shola. At the bottom right, you can see the RL agent playing a game of tag. But these days, the learning agents are using generative models such as LLMs instead of traditional RL methods. So generative agents embody human behavior. So if the agent is a writer, it writes. If the agent is an artist, it paints. And then it can initiate conversations, it can form opinion, it can remember and reflect on what happened the previous day, it can plan for the next day. So the paper here from Stanford on the left, it describes an architecture that extends a LLM to store a complete record of the agent's experiences using natural language in a memory stream. So based on their perceptions, the architecture retrieves all the relevant information from the memory and uses that retrieved memory to determine what is the next action that it has to do. So these retrieved memories are also used to form these long-term memory plans, and then they can create higher level reflections, and then it can be used for future use. So there is also this paper on the right from Google DeepMind that demonstrates an instructable agent that can accomplish anything that a human can do by in any simulated 3D environment. So the agents interact with environments in real time using a generic human-like interface. So the inputs are observations and language instructions, and the outputs are keyboard and mouse actions. So this can easily be extended into a gaming scenario. That's the reason why I wanted to talk about this topic. So since these models are very versatile and can be adopted to perform many tasks, these are generally called as foundational models. So in our team, we built a foundation model that is composed of face animation, body animation, language, large language model, body model, and text-to-speech model. So as the complexity of the NPCs keeps growing, we need to increase personalization. We need to make sure they have realistic textures, clothing. We expect them to demonstrate emergent behaviors. So in this case, the input to our model is composed of images for personalization, text to describe the storyline, action prompts, shape, and gender for the NPC, and audio if there is any human interaction needed with the NPC. An ensemble of the models are used to generate the NPC, voice, and animation. The foundational model generates body shape, appearance of the NPC, conversation, and face and body animation sequences. So these sequences can then be visualized in a game engine. So this is just one example pipeline that we built that we can show how we can create these interactive self-aware agents in a gaming NPC scenario. Okay. Now, let's put this all together. So we want to be able to create action-controllable, persistent, dynamic, interactive worlds which could be described with text, images, photographs, sketches, etc., using AI. And we want to make sure that we preserve the artist's vision in the process. We want precise camera control, and we want this filled with self-aware objects exhibiting emergent behavior. So that's the final ultimate goal of inferred reality. So this is a new paradigm of rendering, and there is some very early research happening in this area, addressing some of these requirements. So I'll reference some of those research papers now. So the first one here on the left is a paper from Google. It's called Genie. It demonstrates an action-controllable virtual world which is described through text, synthetic images, photographs, or even sketches. The input is frames of video tokenized to infer some latent actions, what happens between each frame. And then it is then passed on to a dynamics model, and that generates the next frame in an iterative manner. On the right here is a demonstration from a team at Etched. So they create an interactive, real-time, open-world AI model that takes in keyboard input, and it generates worlds with physics, rules, and graphics. And there is no physics engine involved here at all. So they use spatial autoencoder and a latent diffusion backbone. The third paper here is from Microsoft. So they generate consistent and diverse gameplay sequences that persist with user modifications. A VQ-GAN encodes the image as a sequence of tokens to a compact, discrete, latent representation. And then a causal transformer is then trained to predict the latent observation and discretized action tokens. The final paper here is from NVIDIA. They created a video model with precise camera control and 3D consistency. User input is a single view or a multi-view images or some dynamic videos. And they predict the depth of each of these images and project it to a 3D space, and then build a spatio-temporal cache. And based on the camera poses, they create video sequences, which can then be used to condition their neural network. This can also do some novel view synthesis because they aren't projecting it to the 3D world. So all of these new research techniques are pushing to herald a new paradigm of rendering, which I'm calling it as generative rendering. So imagine if you can just generate a keyframe from a game or a scene, and then the keyframe could be low resolution, low poly, could even be a sketch from an artist. And now if I can augment that with an input seed from a game engine, per frame. And this input could be, depth buffers, edges, skeleton for the actor, whatever, right? Shown in the example. And with the power of Gen AI, if we can generate a temporally stable stream of frames, like the one on the right. I know the mammoth looks horrible, it's like back-combed hair, but, oops. Yeah, so think about it, if we can do this with Gen AI. Imagine building this kind of a pipeline where the game engine gives us the keyframe, some skeleton, or like I said, edge depth, user actions, guiding buffers. Maybe we'll need some radiance cues because we need accurate lighting. And then push it through a Gen AI model, and then generate low resolution but spatially stable, more photorealistic, physically accurate frames out of it. Use an upscale model to upscale it to the resolution that you want. So this takes us to the next paradigm of rendering with Gen AI accelerated rendering. Right? Of course, there are lots of limitations with generative AI at this time. For example, control consistency is a problem. So we need a lot of training data, and we need some extra conditioning to be able to control the hallucinations. Identity consistency, again, a problem. So we need some kind of cross-frame attention. It's definitely not real time at this time, but then there are steps or knobs that we can tune. We can get to linear diffusion, MLA, smaller models, one-step denoising, distillation. We can employ all these methods. You all must have heard about what happened with DeepSeek, where they distilled a huge OpenAI model to something really small that you can run on your mobile phone now. Generalization, again, we need a large data set for this, mixing both synthetic and real-world scenes. Temporal stability is still a question. We probably will need some temporal attentions and warp noise. Preserving artist vision is extremely critical, so improved prompt engineering, and prompt here need not be just text. And then we need extra conditioning. Obviously, there is a big legal black hole here that we need to fill. We need to make sure that there should be good ethical use of these technologies, and where do you get the, when you use a generative AI model, and how you have trained, and what is the data set that was employed to train these models. So a good legal AI policy needs to come into place for the generative rendering to get popular. Okay, so I talked about multiple transformational stages. So again, one size does not fit all. So we encourage the ISVs to consider these techniques as tools in a toolbox and pick the techniques that works best for them. Here are some criteria for the ISVs to consider. Based on the capabilities of the target platform, you may be wanting to run your workload on mobile form factor, maybe on desktop or console, cloud. So some techniques may be applicable, may not be applicable for something like console. Asset availability is another question, like based on your ecosystem requirements. The game engine needs to be neural ready, right? You should be able to consume neural representations. Sometimes it will be a black box. So how easy is it for the ISV to employ such techniques in their rendering pipeline? And then how intrusive can it be, right? That's another question. Also, ability to sustain a training loop. I mentioned some of the techniques I talked about needs online training. So can the ISV sustain a training loop? Where do they get the data from? Ability to have a fallback to a analytical method if you don't want to go the inference way. And then some quality versus performance trade-offs that you would like to make. The other question is, AAA games versus indie games, who would adapt this first? So that's another thing to think about. All right, so here are my call to action. So us as the graphics community, we need to take several steps if you want to get towards inferred reality. So as IHVs, us at AMD, we will be building hardware for PPA efficiency, targeting step 3, 4, and 5. And thankfully, all these 3 steps, they collapse into some kind of generative model. So we need to make sure that diffusion models, transformers, they all run best on our GPU and investigate ways to reduce latency and improve throughput. Maybe work graphs will be a good fit for number 4. And then there is an immediate need to create ML-friendly rendering APIs. We need to come up with standards for neural primitives. Maybe neural representation will become another primitive like a triangle now. And we need to come up with APIs for these agentic interactions. Windows needs to be needs to be a first-class citizen for both training and inference in these scenarios. And we want to ensure that there is confidence in the content that is being used. So the training data needs to be ethically sourced, and it should be copyright, challenge-proof, secure, and the AI policy needs to evolve around that. As always, you can connect with us on GPU Open. We are a very open source friendly company. Most of our research are posted here. And of course, you can connect with me offline if you wish to discuss more about any of these research topics that I discussed here. And that's my presentation.
Thank you, Rama. We have some time for questions, if you have any questions. Ah, there.
Hi, thank you for the presentation. So my question is a bit general, but I remember at the beginning of your presentation, you began with the argument that we are moving towards a neural paradigm because we're running into hardware restrictions in terms of being able to render with traditional methods. And then toward the end, we're talking about generative AI, which, as we all know, has, is extremely hardware intensive and is even, environmentally concerning because of how much energy it uses. How do you reconcile those two problems?
Yeah, good question. So like I said, right, today the ML models on the generative AI side are pretty intensive. I completely agree with that. But there are multiple knobs that we can push to make it run in single step, denoising, or we can distill a smaller model out of it. So these are some of the things that still evolving and maturing, and we are researching on the topic on how can I distill a very small model. Probably even the Microsoft paper that I mentioned, they started off with something like 1.6 billion parameters, and they reduced it to 15 million using distillation process. So these techniques we can employ to bring it to a much smaller footprint than what we currently have.
So I guess just a follow-up question to that then is where is the confidence that these more black box machine learning based models will be able to improve substantially enough to be real time? Where does that confidence come from when compared to the alternative, which is investigating more traditional methods to accomplish the same task?
Yeah, so the ton of training data that it has been trained on, right? That's where the confidence comes from. So today, these models are trained on huge corpus of data. So it can hallucinate whatever that your prompt gives you. And then obviously you will be controlling it using some conditioning buffers, and that's what I demonstrated in the caustics example. So again, this is very early research. We still have a long way to go, and that's why I mentioned, this journey is a multi-year journey to get there. And we don't have to take all the steps here. There could be, we can just stop it at, hey, let me get the costly caustics done using generative AI, and then not go the next mile. But I just wanted to show a vision of, hey, there is a path here where we can get to generative rendering.
Thank you.
Sure.
You'll be next. I want to hook into this really quickly because you talked about controlling hallucinations. Is there a way to bound how wrong a network gets it?
How wrong?
Yes, can you somehow somehow tell us something about, this network might get things wrong some of the time. The caustic might be in the wrong place, so the reflection is too big. But how bad is it, basically?
Yeah, so you can fine-tune the model and then use some loss functions to basically determine what is the acceptable amount of wrong here, right? So you can do comparisons with traditional rendering to like I showed in the example, the reflection of the ring looked bigger than the ring itself, right? So there are some issues and inaccuracies still that is being worked out, but again, loss functions will be a good way to go.
Thanks for sharing your fascinating vision. So at first I was a little bit scared by the idea of having self-aware objects in my game. But then I realized that maybe I didn't fully understand what you mean by self-aware. So maybe you could elaborate.
Yeah. So the example that I showed with the robot, right? Imagine if the robot is self-aware, it understands, it's like a human. It can understand what it is, what its function is, what is it supposed to look like, behave like, interact with the environment. So it's completely aware and it's learning, like a small baby when the baby starts to learn, right? So they start to imitate or get rewarded based on a good behavior. So these days, these kind of objects need not go through the reinforcement learning phase, but there are LLMs and vision language models that we can employ to train these objects and make them as agents that are self-aware. They know how to interact with their world. Does that answer?
Any more questions? All right, so I have one more question, which is, I think that one advantage of some of the traditional rendering methods is that they allow for standardization in some way. So examples would be open shading language or things like that, interfaces. You touched a little bit on this, but are you aware of any standardization processes in the generative domain?
They have started to kick in some of these through, not through Chronos, but other AI policy bodies. But this is like I said, it's a very big area of a big legal loophole at this time. So even when we pick a model to use within research, we always want to make sure that not just the model is compliant for research. We also make sure the data that model was trained on is also okay to use for research. So that's a big policy hole at this time. So we need to work on making sure that policy gets in place before we can make this mainstream.
Any more questions? Well, in that case, let's thank Rama again.
Thank you.
And we will now have a reception, and I believe it's upstairs, so just go up. Yeah.